There is a river in space hundreds of millions of light years long. It is not a galaxy, it is a flow of thin gas and gravity. The immediate takeaway is simple. Space makes patterns before it makes things. Picture a night sky peeled back, revealing soft gradients and faint threads. That is the hidden layout the bright objects sit on. When we stop hunting for isolated objects, we see fields and flows. A field is just a value at every point in space. Temperature, density, velocity, and curvature each draw a quiet map. Those maps guide where galaxies form and how light bends. We will read those maps together, like weather for the cosmos. Bottom line, objects are notes, but the music is the field. Start with a weird thought. The universe is easier to read as a field than as a zoo of things. A field means every location carries a number or a direction. That number can be density, or temperature, or velocity. You care because fields predict motion and light before anything clumps. Gravity and pressure push on fields, and fields push back. Tiny ripples grow where gravity wins, while pressure smooths others. Radiation leaves fingerprints in those ripples as it travels. Example in real terms. The cosmic microwave background is a skywide temperature field. Its ripples are about 1 part in 100,000. Those tiny variations seeded the web of galaxies we see. Satellites trace that pattern with exquisite detail and noise control. Planck stitched the cold and warm patches into a precise map. One sentence recap. Read the field and you forecast the structure that follows. Gas falls inward, heats up, and stretches into threads between clusters. That lace is the cosmic web, a foam of filaments and sheets. The name means exactly this. Most matter lives in extended strands, not in neat islands. This matters because a galaxy inherits its fuel from the strand. It also inherits its neighbors, its spin, and its fate. Gravity drags dark matter into sheets, then funnels it into filaments. Baryons follow, shock, and glow faintly in ultraviolet and X-rays. Flows keep feeding nodes, while feedback blows some gas back out. Example in real terms. Quasar light picks up thousands of tiny absorption lines along the way. That forest maps hydrogen density like a long exposure photograph. Simulations reproduce the same statistics, filament widths, and alignments. Observers now image filaments around clusters at megaparsec scales, so the picture is clear. Galaxies ride on streams carved by the web. Now look at the empty places, the giant black bubbles between threads. Those are cosmic voids, regions with far fewer galaxies than average. A void is just an underdensity spread over tens of megaparsecs. You should care because emptiness magnifies the rules of gravity. Inside a void, space expands a bit faster than average. Matter flows outward along gentle gradients, like air leaving a room. Light also feels the difference and shifts slightly in energy. That shift stacks up across a supervoid and becomes measurable. Example in real terms. Lensing around void edges subtly squeezes background galaxy shapes. Surveys detect that squeeze after stacking thousands of voids together. Temperature maps show small correlations with the largest nearby voids. Those patterns test dark energy and alternative gravity models directly. Net result, even the blanks on the map carry loud information. Switch perspectives to motion, not position, and watch arrows fill the sky. That arrow map is the velocity field, the flow of matter. The definition is simple. Each point has a speed and a direction. It matters for distances, growth rates, and the mass that drives them. Gravity pulls, and overdense regions draw flows inward across many megaparsecs. Underdense regions push matter away, leaving elongated tracks in redshift space. Spectra record those distortions as squashed and stretched clustering patterns. One sentence recap. Those shapes encode how fast structure builds under gravity. Example in real terms. The galaxy surveys show a clear squashing along the line of sight. That Kaiser pattern reveals the growth rate at different cosmic times. Combined with geometry, it pins down a parameter often called F sigma 8. Values land around the mid-0.4s in many analyses. That number checks whether matter clumps as fast as expected. Zoom into light itself and rotate it like a compass across the sky. That rotating pattern is polarization, a field drawn on radiation. The meaning is plain. Polarization marks the direction light waves prefer to oscillate. You care because orientation carries memory of scattering and gravity. Thomson's scattering imprints polarization when light meets moving electrons. Density ripples make curl-free patterns, called E-modes, across the sky. Gravitational lensing then warps those patterns into gentle curls. Those curls are B-modes and they rise on small scales. Example in real terms. Planck mapped E modes across the full microwave sky with precision. Ground telescopes now peel out lensing B modes as clean signals. Claims of primordial B modes met dust, and that lesson stuck. Foregrounds can mimic curls, so careful cleaning is non-negotiable. Bottom line, polarization turns light into a directional field we can read. Let gravity sketch with glass, using galaxies as fuzzy background brush strokes. That sketch is weak lensing, a map of mass through tiny shears. A lensing map means this. You infer the gravitational potential by averaging shape distortions. It matters because mass bends light whether it glows or not. Random galaxies point everywhere, so you need millions for a signal. Correlated stretches reveal where matter piles up into ridges and basins. From that, you reconstruct a convergence field, often called kappa. Tomography slices the field by distance and tracks growth with time. Example in real terms. Recent surveys deliver cosmic shear constraints on clustering strength. Preferred values sit in the mid-0.7 range today. That is slightly lower than some microwave background inferences. Teams cross-check calibrations, redshifts, and models to close the gap. What to remember: lensing turns the invisible potential into a measured map. Trade pictures for counts and let statistics become the main character. The tool here is the correlation function, a measure of pair excess. It just means this: count how often pairs appear at a given separation versus random. You care because averaging melts noise and preserves only the signal. Gravity leaves a preferred scale where sound once rang. That ruler is the baryon acoustic oscillation imprint, about 150 megaparsecs. In Fourier space, the power spectrum carries the same story. Wiggles mark that scale, and their phase pins distances cleanly. Example in real terms. Huge surveys now measure the ruler with percent-level precision. They map expansion history across a wide redshift range directly. Combined with velocity distortions, they test dark energy smoothness. Cross correlations with lensing then sharpen mass growth constraints further. Bottom line, statistics make the field legible, and distances speak. Walk back outside with me and look up without naming things. See flows, gradients, and gentle textures guiding every bright island. The core idea is now familiar. Space is a set of fields that make patterns. That viewpoint matters because it links light, motion, and shape. You can read weather in the sky and forecast what forms next. We traced temperature ripples, filaments, voids, and velocity arrows. We watched light twist into E and B modes, then shear. We counted pairs to reveal rulers and mapped the unseen mass. Each step paid attention to fields first and objects second. One calm promise remains. This habit works in data, in code, and in thought. Start by asking what varies smoothly and what correlates across space. Then ask which process could write that pattern with time. If that clicked, join me for the next deep dive soon.